So let's recap. We have our data, which is all these students. The blue ones have been accepted and the red ones have been rejected. And we have our model, which consists of the equation 2 times test plus grades minus 18, which gives rise to this boundary line, which is the points where the score is 0, and a prediction. The prediction says that the student gets accepted if the score is positive or 0, and rejected if the score is negative. So now we'll introduce the notion of a perceptron, which is the building block of neural networks, and it's just an encoding of our equation into a small graph. The way we build it is the following. Here we have our data and our boundary line, and we fit it inside a node. And now we add small nodes for the inputs, which in this case, they are the test and the grades. Here we can see an example where test equals 7 and grades equals 6. And what the perceptron does is it plots the point 7, 6 and checks if the point is in the positive or negative area. If the point is in the positive area, then it returns a yes. And if it is in the negative area, it returns a no. So let's recall that our equation is score equals 2 times test plus 1 times grade minus 18. And that our prediction consists of accepting the student if the score is positive or 0 and rejecting them if the score is negative. These weights, 2, 1, and minus 18, are what define the linear equation, and so we'll use them as labels in the graph. The 2 and the 1 will label the edges coming from x1 and x2 respectively, and the bias unit minus 18 will label the node. Thus, when we see a node with these labels, we can think of the linear equation they generate. Another way to graph this node is to consider the bias as part of the input. Now, since w1 gets multiplied by x1 and w2 by x2, it's natural to think that b gets multiplied by a 1. So we'll have the b labeling an edge coming from a 1. Then what the node does is it multiplies the values coming from the incoming nodes by the values on the corresponding edges. In this case, that's a 7 times 1, a 6 times 2, and a 1 times minus 18. Then it adds them, and finally it checks if the result is greater than or equal to 0. If it is, then the node returns a yes or a value of 1. And if it isn't, then the node returns a no or a value of 0. In this case, since the equation returns a 1 and that is greater than 0, then this node will return a value of 1, signaling that the student gets accepted. We'll be using both notations throughout this class, although the second one will be used more often. In the general case, this is how the nodes look. We will have our node over here, then n inputs coming in with values x1 up to xn and 1, and edges with weights w1 up to wn and b, corresponding to the bias unit. And then the node calculates the linear equation wx plus b, which is the summation from I equals 1 to n of wixi plus b. This node then checks if the value is 0 or bigger, and if it is, then the node returns a value of 1 for yes, and if not, then it returns a value of 0 for no. Note that we're using an implicit function here, which is called a step function. What the step function does is it returns a 1 if the input is positive or 0, and a 0 if the input is negative. So in reality, these perceptrons can be seen as a combination of nodes, where the first node calculates a linear equation on the inputs on the weights, and the second node applies the step function to the result. These can be graphed as follows. The summation sign represents the linear function in the first node, and the drawing represents the step function in the second node. In the future, we'll use different step functions, so this is why it's useful to specify it in the node. So as we've seen, there are two ways to represent perceptrons. The one on the left has the bias unit coming from an input node with a value of 1, and the one on the right has the bias inside the node.